Hi everyone. Today I'm going to show you how you can simulate a unit cell that is for a periodic surface, basically in ANSYS HFSS. This is a 2020 version. So this kind of simulation is useful when you're trying to simulate a frequency selective surface or design the constituent unit cell for reflectarrays, transmitarrays, or even metasurfaces. So let's just start by opening a project. So once you open ANSYS HFSS, this environment gets opened, and then you can basically click on this plus sign and then right click on it and then say insert HFSS design. So by that, a new file would get inserted in your project. And now you can basically draw your structure and set up your boundary conditions, set up your excitation, and then also get the result, look at the results that you want. So this is our three-dimensional space here. So let's say I'm going to design a unit cell that has some dielectric. So I'm going to do that. I'm going to create a box. And this is simply for a square lattice unit cell. So basically the unit cell gets repeated in X and Y direction. So this is going to be my dielectric. I'm going to parameterize the structure to, for example, minus period over 2, minus period over 2, and then minus H over 2, which is the thickness of this dielectric. And here the period, when you define the period, usually for these kind of surfaces, again, the composing unit cell has to be smaller than lambda over 2 to avoid grading lobes. So for example, if I'm designing for 10 gigahertz, my wavelengths or the wavelengths is going to be 30 millimeter. So that means that the lambda over 2 is going to be 15 millimeter. So I'm going to just put this as, for example, 14 millimeter here. And then for the thickness, I usually use dielectric RT Droid 5880 from Rogers. And then there are some standard thicknesses there. So make sure that once you start designing your unit cell, take a look at these standard thicknesses so that like you don't just put it a random thickness here that you can't fabricate later. So for H, for example, I know that 0.787 millimeter would work because, 1.525 millimeter would work for this thickness. Okay, so then, yes, I'm going to design the period as P, and it's a square lattice, so the same thickness in both directions, and then H here. Okay, then you can press fit all and then look at your dielectric. You can change the color of this dielectric by, for example, this, and then look at it this way. Okay. Now, this is our dielectric. We usually design a scatter on top of this as well. So for now, I'm going to go for a scatter that is going to let the wave, that it becomes transparent at resonance. So I'm going to just design like a circular slot here. I know because slots are basically become transparent unlike patch-based scatterers. So minus P over 2, minus P over 2. And then I'm going to put this on top of the dielectric. So the Z location would be H over 2. So P here, great. Then I'm going to remove, by a slot we mean that we are going to remove a scatter from this. Oops. We are going to remove a shape from this. So it turned out like it's okay. So it became elliptical. That's fine. Major radius. This can be like usually scatters again. They resonate when their effective electrical length is λ/2. So I'm just gonna choose 5 millimeter for this one and 1.5 for the ratio. I don't know, I'm just making, hopefully when you start doing this, you have, this is bigger, you have a reference design that you're going to look at. So I'm gonna go 5 millimeter here, see what happens. Still large, so 4. Anyway, I'm just designing something random here. So once I can subtract these two designs from each other, and then that would make a scatter that looks like an elliptical shape and that is removed from this scatter. So don't forget to assign boundary condition here. So I'm gonna assign perfect electric boundary condition here because I want to assume that this is going to be the metallization on my unit cell. Okay, so I'm not going to get into like how you should design a metasurface. I'm assuming that you have a reference design and you're just trying to simulate what you see in a paper in HFSS. Okay, so and then we can assign material to here. As I said, I'm going to go with Rogers Artidroid 5880, this material. The epsilon R for it is 2.2, which is a kind of like a good epsilon R for these surfaces to reduce reflection from them. Okay, then what we are going to do is we are going to assume that like this unit cell is going to be excited by a plane wave. In order to do that, you need to create a box around this unit cell that stretches from the top and bottom. So let's do that. So again, minus P, it exactly has to be the size of your unit cell, H/2. I'm gonna assign about 15 millimeter λ/2 on top from the surface of this, from the surface of the unit cell. And then λ/4 would work too, but I'm just making sure that all the evanescent modes are disappearing before it reaches my unit cell here. And then H plus 30 millimeter. Okay. Oops. Something happened. Yes, there should have been a minus sign here. Okay. So in order to see what's inside here, I'm gonna put display wireframe. So now I can see what is happening inside this air box. Leave this as vacuum because this is, you are going to assume that your metasurface or your surface, electromagnetic surface is in air. Okay, then this is a good point to save your project in case something happens. I'm gonna call this transparent unit cell. Okay, so what is left, you can check this, like you can check what is left here basically by looking at validate. It says you're missing boundary conditions, excitation, and then you didn't tell HFSS what you're trying to do, what you're trying to examine about this structure. So let's start by excitation. So once you can click on F or hold F, and then it would allow you to select surfaces here. For example, I can select this surface or this. So press F, and then you can select surfaces on your structure, on your geometry. So I'm gonna assign this one. I'm assuming that the incident wave is coming from the top and it is going to be received on the other side of this metasurface. So let's say this is my first excitation. And then for this kind of unit cells, you have to go to Fluke port. Then you have to assign the direction of your electric field. So usually we have two directions. One of them is TE and the other one is transverse. TE means transverse electric field, and the other one is TM, which is transverse magnetic field. For normal incidence, this doesn't matter which direction you're assigning. So I'm just assigning something here. But that means that my first mode here, for first mode of the excitation is going to be in Y direction, and the other one is going to be in X direction. Okay. So here, as you can see, the two polarizations are stated here. Number of modes is 2. Because my unit cell is less than lambda over 2, the excitations that are going to be able to propagate through this kind of like looking like a waveguide is going to be only the fundamental modes. If your unit cell is larger than lambda over 2, then you have to increase these number of modes to allow the higher order modes to propagate. Otherwise, HFSS would make a mistake, assuming that these two fundamental modes are all of your modes that can propagate through the waveguide, and then it would just make the calculations for the power balance wrong. So yes, remember that if your unit cell is not lambda over 2 or larger than lambda over 2, this number of modes has to be larger. Okay, do not forget to embed your results, because especially when you're designing phased array, transmit array, or reflectarray unit cell, you are trying to see how the phase of your unit cell or how your unit cell is changing the phase of the incoming wave. And in order to calculate that correctly, you have to de-embed this. So I'm going to de-embed it exactly to the distance between the fluid port and to the beginning of my unit cell, which was 15 millimeter. Next, and then finish. So if you look here, you can see excitations. You can see that this is de-embedded exactly to the top of the unit cell. So now what we're going to try is to repeat this to the other side too. So you can press Alt and then also left click and then rotate this. If not, you can go to model or draw here and then keep this guy and then rotate your structure by holding the left click as well. Okay, escape. I'm gonna choose this surface now. I'm gonna assign another fluid port as my receiving port here. Sorry, excitation, and then fluid port here. And then now the directions of the electric field get defined. So do not remember to de-embed here, again, 15 millimeter. Okay, great. Now I'm gonna choose the orientation of this unit cell. Again, let's save so that we don't lose our progress up to here. Then, so we were missing excitation, boundary conditions, and also setup. So we set up our excitation. Now it's time for boundary condition. So depending on your ANSYS HFSS version here, there are two types of, basically, there are different types of like units, periodic boundary conditions that you can assign. So these has to be, the size of your unit cell should represent or imply that your unit cell is going to be repeated in X and Y direction. So this is what we're going to do. Right click, oops, select the surface, right click on it, and then assign boundary. And then here in the new version, it says coupled. Previously, it was, here is primary and secondary. In the previous versions, it was, I think it was master and slave, just to show that like these two are coupled to each other. So we're gonna go with primary here. These vectors are important. So you're assigning the vector that this boundary is going to be aligned with. So new vector. Make sure you see this square, which means that you are getting the corner of that face basically. So click, and then let's go to the other corner. So the two vectors of UV should be lying on this surface. Okay, now we're gonna assign the other boundary on the other side, which is the secondary of this boundary condition. So assign boundary coupled, then secondary, then the primary, we are gonna assign it to primary 1, which is right in front of it. So remember, it has to be, each primary and secondary pair are going to be in front of each other. Then new vector, and you're gonna get, again, a square, square, great. Phi and theta here are showing if you want to excite this unit cell with oblique incidence or normal incidence. So I'm going to set them as 0, 0, which means normal incidence. But for example, imagine if I put 30° here, now you can see that this vector gets tilted. You see this red one in the middle? That means that now my excitation is coming with an oblique incidence angled at 30°. You can even change this one, for example, 90°, and now it's going to lie in YZ direction. So for now, I'm going to set it as 0. If you would like to see the performance of your unit cell under oblique incidence and normal incidence, what you can do is to parameterize these theta inc, incident, phi inc, and then basically set them as parameters. So if you go to finish, it's going to ask you, so I'm going to set this as 0 and then also 0. So this is going to be normal incidence. Okay. Now it doesn't matter which face you pick, just pick one of the other remaining faces here. So I'm going to put this one as coupled and then primary. So the same story, again, we're going to get this direction doesn't matter. Just make sure that you're seeing this as square, meaning that you're getting the corner. Otherwise, HFSS would throw you an error. Now, oops. Right in front of it, assign boundary coupled the secondary one. Now we are going to assign right in front of it primary 2 as the one that we want to link this secondary boundary condition to it. And then again, we are going from here to here. Okay, great. So this is would be automatically assigned here. So once you change the theta and phi angle for one of these boundary conditions, for the other one automatically changes. Okay, so now if you look at this, it's going to say you haven't set up analysis set up here. So that's the only thing is left. So let's save. Then you can see the boundaries here, our scatterer, our primary, secondaries, primary 2. So now every side has something assigned to it. That's the way it should be. So analysis, and then I said I'm gonna assign this for 10 gigahertz. So let's go to 10 gigahertz here. Number of passes, maximum number of passes. Make sure that this number is large because, for example, if you say maximum number of 6, number of passes to be 6, once HFSS runs 6 passes, no matter if it converges to a good result or not, it's going to stop. So I'm going to set this as 30, and then maximum delta as 0.02. If the default value is okay, then the option here. What is the difference between all of these different things here? The domain of composition is when you have 2 different domains at least. So when, for example, it is used when you want to run finite element, integral boundary condition, when you have some vacuum in the middle of your structure that you don't want to mesh it. So it saves you some memory, which is not applicable here because our domain is just 1. But you can go to iterative solver here. It will save you some memory. So iterative solver saves you some memory. And then 30% for mesh refinement is okay. Minimum number of passes. Again, this is not as critical as the maximum number, but you can make sure that your results are good by increasing this number. Something else I would recommend is changing this minimum number of converged passes to at least 3. One would mean that if your result gets converged for only one pass, even if it is an accidental convergence, again, HFSS stops. So you want to make sure that this is not an accidental good result. So increase it to 3 just to make sure that everything is working. Then, yeah, for example, you can run a sweep, for example, let's say from 8 gigahertz to 12 gigahertz, depending on, again, this is probably is given to you by your application, your customer, your, I don't know, paper. So here I'm going to set this to 41. So these are the different things. So discrete is the slowest one. It's not necessary for this type of simulation. Usually you would set up a discrete frequency sweep when you want to look at the radiation pattern of your antenna or something like that, because it's very slow. And like, if you're interested to look at every frequency, then in that case, you should choose it. Otherwise, it would waste your time. Interpolation is very good one, it's fast. I wouldn't recommend this one. It's too fast. It might not be as accurate. So you can go to interpolation. So let's set it as okay. Here, everything is okay. Let's save it. So we can now run this setup by going right click on it and says analyze. So this would start the simulation. It might take a minute here, but you can prepare what you want to look at. So we want to look at if I have an electric field that is going in this direction, at what frequency this structure would allow it to pass through. So one of the parameters you should look at, the interesting parameters here are scattering parameters. For example, S11, S21, and things like that. And in order to read these, we can go or look at them. You can go right click, create modal solution data report, rectangular plot. And then here, you would see all kinds of scattering parameters here. What does this mean? So here, basically, you have to be able to translate these. So it says that a scattering parameter from fluid port mode 1 to fluid port 1 mode 1 is this parameter, right? This is basically when you see these two, the first one and the third one matching each other, that means reflection coefficient, because you're looking at the parameter that is being transmitted from port 1, for example, and being received as port 1. That's the definition of reflection coefficient. Now, the second and the fourth one shows you the mode. So for example, here, the first one and the second one shows you mode 1 being transmitted and is being received as mode 1. So that's the reflection coefficient when your when your incident field is in Y direction, if you remember. Now, for example, how do I look at the transmission coefficient? So transmission coefficient, for example, can be wherever your first and third parameter are not equal. So for example, here, look at this one. This says the scattering parameter at port 2 was transmitted and at port 1 is being received. And the mode is 1, 1. So this is what we call the copolarized transmission coefficient for an electric field that is in Y direction. So I'm interested in this one. And then there is another one, 2, 2, 1, 2. 2, 2, 1, 2, where are you? Here. This is the transmission coefficient for the second mode, which is in X direction. So I'm going to look at these two. Okay. Because I chose an elliptical design here, you would expect that this structure would not be seen the same for an electric field in X direction and Y direction. So that's why the transmission coefficient is different. It is not quite transparent yet. You can see at higher frequency, it becomes transparent. So I my unit cell is quite actually small for now, and for it to become transparent. But if I wanted to look at the reflection coefficients here, for example, I could go to S111. This first one would show me the reflection coefficient for mode 1. And then I want to look at the reflection coefficient for mode 2 here, which is 1, 2, 1, 2. 1, 2, 1, 2. Exactly this one. So these are my reflection coefficients. So as you can see, it's very reflective for mode 1, which is in Y direction. If you forget what is mode 1, what is mode 2, here, come here for liquid port, mode 1, and says zoom to the region. Then you would go to the structure, and then you would see that, for example, here, mode 1 is in Y direction. You can look at it from the top here. Mode 2 is in X direction. Okay, so I think that's it for the unit cell. Then it becomes more like, for example, you can set up parametric sweep, or you can look at the excitations of, oops, where did it go? You can look at the excitation of, I don't know why this keeps disappearing on me, but yeah, you can look at the phase response and things like that. For example, for phase, you can go to phase of angle degree, phase of reflection coefficient for mode 1, and then you would see the phase of it. Okay, thank you very much. And this is it on a unit cell.